Right, hello A2. This is feedback on the Key Assessment 1 Rates of Reactions paper. I have to say that overall I wasn't very happy with the results, and I don't think you will be either. So it's very important that you look at this feedback, that you take on board what I'm talking about here, that you make the corrections on your work, and that you do some more examples of these kinds of questions. It's not going to get any easier. Okay, so question 1, you're given initial rates data. You're asked to analyse and interpret the results, analyse them, obviously break them down, interpret them to deduce the order of reaction of each reactant, and explain your reasoning. Now, the best way to do this is to be very methodical. You look at it, find something where the concentration is the same and the other concentration is changing. So experiments 1 and 2, you can see that the concentration of O3 is increasing by 4, and so is the rate. So that means that obviously this is first order with respect to O3. And if we look at experiments 2 and 3, we can see that the concentration of O3 is increasing by 2, but so is C2H4. Now, the rate is shown as increasing by 4, from 4 to 16. Now, we know that with respect to O3, it's first order, yeah? So we would expect it to double, because that's what's happened with O3. It's doubled, we would expect the rate to double, and it doesn't. It quadruples. So the other doubling effect has come from the C2H4, which means that we also have first order for C2H4. Now, you need to be able to explain this clearly. It's quite categoric, and lots of A2 questions are like this, where they want a clear explanation. And then don't forget to write the rate. Once you've deduced the orders, write the rate equation. Okay, then you're asked to calculate the value of the rate constant, which is pretty straightforward, providing you've got your rate equation correct and the units. So I've just done a quick example there of, if you're not sure about units, you can have a look at that. Right, deduce the initial rate of formation of oxygen, not ozone this time. Obviously, we've been talking about ozone previously. Now we're looking at oxygen in experiment 1. So the crucial thing is, if we go back up to the chemical equation, we're actually looking at the formation of this, of methanol. Yeah, so these rates are not related to oxygen, they're related to methanol. But we just need to look at the ratio here. So it's 4 to 1. Yeah. Okay, let's go back down. So if it's the ratio is 4 to 1, methanol to oxygen, therefore you obviously divide the rate for the formation of methanol by 4, which gives us the answer. It's only 1 mark, so it's kind of telling you that it's a pretty straightforward calculation. And this one, so many of you didn't get this 1 mark, and you can't afford to lose 1 mark because you didn't actually mention both parts of the question, where it says the rate of reaction and the value of the rate constant. So you happily said it would increase the rate of reaction, but you didn't also say that it would also increase K. Okay. Right, question 2. This one was very badly done because most of you didn't use the graph in your answer. So this graph is given to you for a reason. That you're not going to be given information in a question like this that you're not going to use. So this should have rung some kind of alarm bells, or put some question mark in your head. The fact that you were given the same concentration for this reactant, yeah? And here we are, hey presto, here's our graph. So this shape, and you must know the shapes of your graphs, yeah, should shout to you that this is going to be a half-life graph. Now, you can very easily see the half-life. Yeah, no, there are no values here, you're quite right, but there's 1, 2, 3, 4, 5, 6 rectangles, so you just halve them, yeah? So this is first order with respect to propanone, and then we can then deduce the other two. So we know that propanone is first order, iodine, double the rate, double the concentration, and the rate stays the same. So that's zero order, so we don't need to include that in the rate equation. But when H plus doubles, the rate doubles, so that's first order with respect to H plus. Now this, what I've written here, really is the reasoning bit that goes in here. So if you're going to get the 6 marks that are actually allocated to this part of the question, what conclusions can be drawn about the kinetics of this reaction from the student's investigation justify your reasoning? The reasoning I've just given you needs to go in here in a coherent, you know, in good English, written properly using scientific terminology. And then obviously if you've got the right rate equation, there shouldn't be a problem calculating the rate constant. The rate equation, actually, I've written it here, but it should go down here. It's included in with the 4 marks that you get for this calculation. So the rate equation, and then the calculation, and the units, okay? And finally here, the rate determining step. So the rate determining step will always have the species in the rate equation. So if you've got your rate equation right, then you stand a good chance. If you haven't, then you're not going to get this right. So we need to come back to this equation. This is our chemical equation. So you're going to start with your species from the rate equation. There isn't really much we can kind of make from this, is there? So if you just stick that hydrogen in there and give it a plus, okay? Okay, that seems like a fair enough intermediate species. Yeah. Now, as it's an intermediate, because it's not in our final equation, we need to have it on this side as well, so we can cancel it. Now we've got the propanone is here in our first rate determining step. We don't need to include it again because we only need 1 molecule. But we do need to have I2, so I2 must go in here in the next part of the mechanism, the second step. Okay, so then we can make our product, iodopropane, and we also need HI. But we need to have an H plus here to cancel this one, this original one in our rate determining step. Yeah. So we need an H plus in there, and we have an HI, and then everything balances nicely. Okay, and that would be 14 marks. So I would say that most of you got 0 marks on this question because you didn't give a coherent explanation. Some of you, hardly any of you used the half-life graph. I think only 1 person used the half-life graph. So you need to get your act together a bit on writing explanations for answers. But this one was pretty straightforward, and most of you did okay on this. Again, just be methodical in the way that you write out your answer. Look at experiments 1 and 2, look at experiments 2 and 3, give a clear explanation what you're looking at and what evidence there is. Our concentration of A increases by 3, the rate increases by 9, therefore we know it's second order, and so on. And then we come up with our rate equation. So that's 3 marks for that question. Okay, this one wasn't very well done. This part of this question, hydrogen peroxide decomposes from water and oxygen. Suggest a method. Now, you should by now be able to recognise that if a gas is produced in a reaction, then that's going to be a good way of following that reaction by collecting the amount of gas. But you must, of course, be measuring the amount of gas using some kind of measurement of time, because otherwise you won't be able to calculate a rate. Yeah, so you can collect gas in various ways: gas syringe, over water, mass loss, whatever. It doesn't matter what you said, but you did also have to include the regular time interval. So some of you only got 1 mark for that. Okay, this is basically just knowing the definition for first order. You should all have got that right, but not everybody did. If the overall order is 1, well, you can only have 1 species in there that can have an order 1, yeah? Because the overall order is made up from adding the order of all the reactants. Okay, and this is recognizing that how would you use a graph of hydrogen peroxide concentration against time to show that the reaction is first order, that you would measure the half-lives. If you've got constant half-life, then it's first order. Okay. Right, yeah, some of you fell down on this, and you shouldn't really, drawing a Boltzmann distribution and then just giving a quick explanation. You know, it's 4 marks. You get most of them from doing the correct drawing. You're looking at temperature change, you know, so your initial one, your initial curve, and then the molecules with the above the activation energy that will react, and then increasing the temperature, shifting the curve over to the right, making it lower. Now, it's very important that you don't put the end of they don't have to meet the x-axis. That's very important that they don't meet the x-axis, but they do need to be reasonably close together and not floating about up here somewhere, which some of you are doing. That's not an accurate depiction of a Boltzmann distribution. Obviously, we need it to start at 0. Okay. And then just label it as to, you know, what you're showing. But some of you didn't even mark activation energy on there. The crucial thing is, you know, the reason that temperature is makes such a big difference to the rate is because it increases the number of molecules or particles that have the required activation energy by an exponential factor. Yeah, and this graph depicts that. Okay, and then you were asked to plot this graph. Now, I've done it in biro because I want you to be able to see it on here, but you should not be plotting the graph with a pen. I've made that absolutely clear, and I think at least 2, if not 3 of you did that in your test. Very important that you label the axes on your graph, that you use sensible scale so you get a nice big plot, you know, as big as possible. And then we're using this equation, yeah, to calculate our activation energy. And it does say here, you include the sign and units, and your answer should be given to 2 significant figures. So some of you lost marks on that because you gave it to 3 significant figures. And make sure that you put the units in with joules. If you left it in joules, fine, or kilojoules. So you should be clear on how to calculate a gradient now. Times it by the gas constant, and that gives you your activation energy. Okay. Right. Oh, sorry. Ignore this page. I've scanned it in twice. Right. And I think we're coming to the last question now. Okay. So we're looking at ammonium cyanate turning into urea in an aqueous solution. Okay, so this is a pretty straightforward calculation, but here some of you got this wrong. So obviously 20.3 was your final volume, so you take that away from it, this number away from it. Okay, that's for 1 mark. Right, and again, I've plotted this graph using red biro, but I wouldn't expect to see you doing it in biro. Yeah, so straightforward graph to plot, very easy. The point being that this shape graph is telling you that you should be looking at half-life again. And in fact, this question here asks you to show 3 successive half-life measurements. So you should have them on your graph. Before that, what is this M final minus MT? Yeah, what term in the rate equation is it proportional to? It's obviously the concentration of ammonium cyanate. You only had ammonium cyanate in your reaction, and the concentration of it is decreasing. Yeah, so that's what it's proportional to. You measure your 3 half-lives. Now, I cannot square up my half-life measurements with the mark scheme. So I think the mark scheme, there's something wrong with the mark scheme because I can't see how they've come up with their values. To me, it's pretty clear. The half-life is increasing. It is not constant, so that's telling you this is not first order. Okay. I mean, it has actually doubled from here to here. Technically, it should have doubled from here to here, but it didn't. So, but we can make an assumption, because in the A level, you're not expected to go above second order, that if it's not first order, it's going to be second order. Okay. Your reasoning is that the half-lives are not constant, and that then gives you the rate equation, definition again for the rate determining step. And then this last question, which is quite common, yeah, comes up commonly. There's a lot of water involved, so should it be involved in the rate equation or the order? But obviously not, because it's so massively much more water than there is ammonium cyanate. You've got 0.35 moles of ammonium cyanate, 55.5 moles of water. Because it is in such excess, the concentration is not really going to change from 55.5. You know, it would be such a small difference that it's not going to affect our calculation at all. So the only thing that is really changing concentration is the ammonium cyanate. So the order that you come up with is with respect to ammonium cyanate only. Okay, so that's it for this key assessment. I will be talking to you about it in class, but I will expect you to have watched this video and made changes on your scripts. Okay, see you soon. Bye.